Thank you for inviting me to this very interesting conference. I'm very happy to be here. So, I first want to show you what I want to do. I give a short introduction. Then I want to say a little bit about the physical background of this theme. The injurious effects of noise have been contributed today already very intensively, so I can skip this a little bit. I will tell a little bit about the legal regulations and also about some specified standards in Europe. Then I go to the reduction possibilities which indeed exist and to the technical realization, and at last I have a point, the calculation of some effects. And then the conclusions. At first I can say this has also been defined what sound and what noise is, and I can say, you can see here the noise effects, some physical, psychological, and social or economical meanings. So now the number first, as an introduction, I put these questions. You see, when I put these questions, how many human lives can be saved? Oh, that's very big, human lives. For how many people life quality can be improved so that it is really noticeable? Which economical costs can be saved? And what is the individual improvement for every single person or every one of us? They're very big questions. And I can say this presentation cannot give an accurate answer to all these questions, but yeah, and the meaning is that all these calculations can be done only statistically. There is only a few calculations which can be done very exactly, but I try to introduce to some estimate calculations which show us how we can come closer to the solution of these questions, to the answers. So there's a short introduction of me. Maybe you do not know about the city of Oldenburg, a very small city, 150,000 people in the north of Germany. This is the North Sea coast, and so you can find it. We have several campuses close around to Oldenburg, and what's important here, I'm working in the physics laboratory, and we do some research in different fields in energy saving, heat protection, climate protection, and also the sustainable construction certification, aeration, solar technology and water treatment, and sound technology and emission protection. This is what brought me to this point here. Okay, now at first, what is to the physical background? You see, a little bit I want to tell about that. I'm not sure what your background is, so I prepared all these items. The first, I can say, when we have sound, we have a tone. This is like one single sine tone. We have sound, this normally we call sound. This is not a sine. This is like ah or oo. There are different sine tones combined. And then we have one single pulse. This is like this. I hope you are now you're awake now after meal. And this is the statistic sound. This is and we heard already about that. For example, when we have these wind generators, we have not a pure statistic sound like from the wind or from a rain. I cannot do this so good, but this is what Ea told. Yeah, okay, Ea was it. You told about the. Oh, sorry, you told about the. This is Ea. Yeah, okay, sorry. This is my. This and there is a tone overlaid to this statistic sound, and this is very bad for our ear and for our soul to govern with that. But I now concentrate on traffic noise, and traffic noise has the same. You have the background from the cars that are far away, then the car comes closer. I don't know that. And this also, when it does not stop all day and night. It's very bad, and you get angry about that. Okay, this is just to show. Here's shown how many people are feeling annoyed by these different types of noise. I did not translate that this is a street, the airplane, the railway, industry, neighborhood, and sports. So now to the physical background. I bomb you with formulas, which is important because to define which is the equivalent sound level and why we can do this, and also can set up some threshold levels, we must at first define what is equivalent sound level is. We have the acoustic energy, for example, of such one single pulse or of a number of pulses. When I divide this, oh, this is a mistake. Sorry, I must divide the energy by the time, not multiply. Oh, sorry, you must correct in your papers. This is E divided by T. This is the acoustic power. Now I have the acoustic power, and with the acoustic power I can define two things. The intensity is the acoustic power related to the surface. And I can say the acoustic power, the intensity is, has a specified relation to the sound pressure when the sound energy travels or runs vertically to the surface which I take in consideration. Then it's very easy. This is written here for defining the power level, the LW. I need a reference power. This is the P0, 10 to the minus 12 watt. And then I can define how much acoustic power comes from any machine or any car which is driving along, or airplane or something like that. The other thing what I can, with this intensity, I can calculate the sound level, and you see the sound level can be calculated by the intensity and also by the sound pressure. Now the equivalent intensity, you see, this is the complete acoustic energy. There is the same mistake. This must not be multiplied. Oh, sorry. This is the complete acoustic energy, not multiplied by the time. And this is being divided by the surface. I get the the equivalent intensity, and with the equivalent intensity correlated to the reference intensity, I can get the equivalent level. This means I take some time, for example, 10 seconds. And when within this 10 seconds I have a long time with a loud sound and a long time with a very low sound, the complete acoustic energy is summed out, is integrated, and then divided by the time again. Okay, this is the same. It must be not multiplied, but divided by the time. So this is a physical background, but I think this is not so interesting as this scale which I set up. I'm now at the point injurious effects of noise, because when I put this intensity or the pressure, both can be correlated to another, and I define the level. Sorry, I go back once. So here I have the sound level, which is the logarithm of the quotient of intensity, of the actual intensity, and the reference intensity. So with this, I can define how much the sound will affect me or any other person. And normally we need only this scale from 0 to 120. I also put 150 into this scale. And you see this green area, that is the area in which we normally live. Yellow is problematic and red is not allowed. That's very easy. The blue area normally doesn't occur because it is all the time. It is more silent than this level, or I must say not more than 30, but you will never or hardly any time have less than 20 decibel, for example, in a living room or in a bedroom, because in this area already the calm breathing is. So when two persons are in one room and both do not stop their breath, you will hear a sound, you will have a sound level of 20 dB. When everything is switched off, for example, in a special cabin, you can have also a level up down to 0, and there you can test how good your ears are. So, but normally we will have this 30 degree. This is this which we need for the nocturnal relaxation. And the danger here is listed, the limit for nocturnal relaxation, and the danger which occurs when we exceed this limit is sleeplessness. This means, and we heard this today already, that when overnight you have more than 30 decibel, you will not have a really relaxing sleep. Sometimes it happens you wake up, and this waking up is a countable number which can give an accurate or a number value to decide how the annoyance is, even if we have not a high level but a low level in the night. The reason of this sound is, I said 20 dB is calm breathing, 30 is a rural background in a village, 50 is about the normal level in an office or the normal urban background, and you need maximum 60 dB for concentration or for to make a rest, to recreate. And there is one very important thing. But I will skip the next slides a little bit faster. We'll see that this 60 is very important for the time, for a long time to have when you have short time more than 90 dB. 90, you see here, is the limit for ear protection. You need this when you have more than, by German law, more than 85. The danger is a hearing defect if you have it every day for a long time. And this noise comes from machines or is normally in a workshop, for example. Also, machines is also in a car, in a freight car, for example. A lecture like this, normally you have about 70 decibel. And also in a shop or in a city, you have this about 70. Now I can go a little bit quicker. Very loud machines or technical processes like forging, for example, or when you have an accident outside, you have levels up to 100, and from 120 on, you have pain in the ear, and also a distinction of the hearing. The danger is the partial deafness. Normally, when you have 120 for some minutes or maybe a little bit longer, we also heard this morning. And when you go still 1,000 times higher, when the intensity is still 1,000 times, 30 decibel is the factor of 1,000 in the intensity. Here, 1,000. This is, you see, this is 20 Pascal. The pressure that is relative low compared with the air pressure. We have 100,000 Pascal here, and only 20 Pascal is so loud that you can not more understand any word which is spoken louder than 120 dB. By 1,000 times higher level, you have the danger of consciousness. Normally you break down then under this noise. You will be deaf at the moment for a long time or forever. And this comes, for example, from explosions. If you're close to explosion, we also already heard about shots. A shot outside a room is not so dangerous, but when you make a shot with a pistol or a gun inside a room, you have a 130 or something like that, and have, in any case, a partial deafness if you have no air protection. So, I think you have this in your papers. So I can come to this first point, this level of 30, then I go to the level of 60, and then of the 90 dB. We heard already in the bedroom you need this 30 dB. When you sleep with open window, so this has been talking about today, and you have the 40 decibel outside by the wall and the open window, you normally have about 10 dB less when it is wide open. So that you can say when you have the idea or when you want to keep your window open in a normal living area, you must make sure that the outside level is not more than 40 dB. Now the 60 dB are dangerous. This is written here, are dangerous for the heart. Here is the heart with the coronary vessels around that, and these coronary vessels must provide the heart with blood, with oxygen, and with sugar, and or other with energy. You must say with energy for, let's say, 80 or 90 or maybe 100 years. And there is a problem if the pressure of the blood is too high, then this will break down. This providing breaks down, and you get a cardiac infarct. And now the question, is this really connected? And I investigated that, and I found that some other speakers are much better informed than me. You saw I'm not a physician, I'm a physicist, and I just found that at a level from rising at a level of about 60 to 80 dB, the blood pressure statistically rises, and here's the annoyance, the strength of annoyance written, and you also see that in this region about 60, the measurable annoyance rises very quick. And this means that we have really not a big, but we have a definable, statistical, measurable danger of infarctus. What is the English? Infarct. I think you understand that. Due to the noise level of more than 60 dB, when you have this noise level all the time. This means also in the night. When we see that from all reasons to die, the cardiovascular diseases are the biggest part. This is cancer and this is cardiovascular, and we have only a few % of this, and in Germany we have about 1 million people dying per year, and for example 1% of this, these are 10,000 people. So I can correlate the death of 10,000 people to, that's a very rough, to the 10,000 people dying because of too high sound level. I'm not sure about that, but that's the idea. I think surely we are in the region of some thousand people could be saved if everybody in Germany, for example, 80 million people, could be saved from too high sound levels in the region of over 60 decibel all over the day. So the next step is 90. Sorry, this is still on to the 60. I added this, you have it not in the papers. There is some possibility to calculate the risk of cardiovascular diseases, and here again it's the level. Here's a level written down, and it has been asked how can we measure whether some people is annoyed, and for example, here are some. Here's written down how many of these people start with any actions to provide the noise. For example, putting ear protection or closing the window, buying noise protection window, or even buying medicine against head pain or something like that. And this again starts in the region of 60 dB, and here we also have the 60 dB level where it is shifted. And you see, and the people are annoyed by a level of about 70 dB when it is in the day, and already at less than 60 dB when it is in the night. So the 90 dB directly goes to the hearing system. I also must not say so much. We heard about this. This is the inner ear with the in Germany we call it Hörschnecke, but cochlea, okay. And we saw about the problems where the hearing curve is getting much bad. It's here the level is written which you need to hear something, and when you have a bad hearing in the region of 4 kilohertz, what we saw 2 times today already, this goes up in the setup or in the finding of this, in the measuring of this hearing capacity. Okay, this is also not so my theme. I just wanted to show this to explain why we have this very simple idea. We have 30, 60, 90 decibel as limits, as threshold values. Now, from these threshold values, some other values are derived. And in Germany, I can say we have we apply some standards or norms, and we have also some legal regulations. And this is the German emission protection law. Now it is Bundesemissionsschutzgesetz, and we like to abbreviate that BIMSCH. And this law says that all over the emission, this can also be vibration or dust or gases or in the air or something like that. That this all shall be regulated by Verordnung. And I don't know the English word for Verordnung. This is not a law, this is under a law, this is more technical. But from the government and the number 16 Verordnung, the BIMSCH, Bundesemissionsschutzverordnung, BIMSCH-V, sorry, we say BIMSCH-V. This regulates how high the level in the day and in the night may be. This is not directly the same as in the standards which we apply, and but you can see in pure and common residual areas, living areas and villages, in the day maximum is allowed 59, in the night 49 dB. This is normally, I must say, a little bit too high. I can show that 40 dB is the threshold where you can sleep with an open window, but we see a little bit later when you do not keep the window wide open, but only a slit or a slot open, then you can sleep with an open window also at 49 dB outside. So, and for in other areas, mixed areas and city areas, you have higher level. This is 5. You have steps of 5 dB. Maybe you notice that many, or almost in any time, the steps are 5 dB steps, because 1 dB hardly can be noticed. The 3 dB means a double of the noise or sound intensity, and the 5 dB is really good to notice, and 10 dB is much higher. So the 5 dB steps are really practicable. The next 5 dB step goes to the working areas, where also we see in the night it is allowed to have 60 dB, and who has his house, his home in a working area, for example, the housekeeper of a factory or something like that, or the owner of a factory. He must live with the situation that on the day he has 70 decibel and in the night he has 60, so he cannot sleep with open window. Other part of the legal regulations, I must see, I think I have still 10 or 15 minutes, is that right? Yeah, okay. I will not explain it too long. This is the method how to calculate this level which will occur from traffic. And we see there is one level which is calculated by this formula, and normally for a street where one car is passing in 1 hour in 25-meter distance, we have a value of 37 dB. This means only one time in an hour the car is going along, and then it's calm. You hear it normally when it's very, very calm, and one car drives along street, a long straight street. You hear it about 2 minutes before it comes, and when it passes, you hear it another 3 or 4 minutes. So when you add the 2 minutes before and 4 minutes after, you have 6 minutes. This is 10% of 1 hour. You hear this, and at this time, the energy, which I call the sound energy, is being integrated for the complete hour. And this, I must say, this car drives with a 100 kilometers per hour in 25 meters distance. Now, from this, you can calculate what happens when you have 2 cars. You have the double energy, you have 3 decibel more, and so on. And you can calculate for the distance, for different distances, how loud this street is for different velocities. See, this is for one car, this is for the velocity, this is for the distance, this is for the street surface, and this is for the rising of the street. Normally, the street surface is flat surface, so it is 0, and if we have no rising or falling of the street, we have here also 0. We have here another thing which we see in the next slide, and again I have this formula here. We have 0 up to minus 4.8 for meteorology meanings. This means it can be louder due to rain or wind coming from the street or going to the street. It's not so loud. And okay, this is for the distance. This is for traffic lights. There we have a traffic light in the crossroad. And this is a part for the structures or buildings between the street and the point where I measure. And this is the important thing. I here now can say by these things we can diminish the noise of the street, because when we take these calculations, a normal street in 25 meters is too loud to sleep there normally. And when I speak now about the reduction possibilities, I must say we have 3 possibilities at the source itself, on the way, and directly before reception. I just exclude this when I close my ears or put some knobs into the ear, some noise noise protections. This is a possibility, but I do not discuss about this now. At the source, there's especially the car can have an exhaust, a noise diminisher, and we can have other tires on the cars, and you can have other street surface and so on. But important is on the way, what happens there. And we have then, on the way, I can say we have two possibilities. The one is what I told, we have some barriers that can be houses or extra barriers like walls or ramparts or something like that. And we can also reduce the noise by distance. And here I have outlined the possibility to reduce for one line is for industrial noise and one is for traffic noise. A traffic noise is a line source. And when you have a line source, the noise is not be reduced so strong by the distance as when I have a point source. Point source is, for example, the wind energy converter or wind generator. And so we can see that when we have in a specified distance, I took, for example, one here in, let's say, 5 meters, we have 75 dB. Then it goes down very fast, and this important value of 60 dB is reached here at 20 meters. To reach this 20 dB, this 6 dB, sorry, for a street in a distance of 5 meters, for example, this at the side of the street, where it is possible to construct a noise barrier, a wall. When you measure here at this point, 75 dB, it takes 100 meters until this is reduced to 60 dB, from 75 to 60. This can be calculated by these formulas, and I think many of you know this or do these calculations yourself. And now the second possibility is to construct barriers. And everybody knows that it is, or not maybe everybody knows that it is good to put this barrier close to the street, to the source, or close to the emission point. Here, in this situation, when you want to put a noise barrier here in front of the house, it's very difficult because it must be higher than the direct connection between the source and the emission point. And for a lower emission point, a window here, for example, in only 2 or 3 meter height, we can see that noise barrier is also effective when I put it directly here to the house or to the living or dwelling point. Here I have the distance. I choose to just a distance of 100 meters and shifted the barrier from, I think, 3 to 97 meters. And you see that at the 3 meters, which is the nearest possible. You cannot put the barrier on the street. That's not possible. But 3 meters is possible. Then you have, for example, in this example, you have 13 dB. When you shift it to the middle between the house and the street, it gets lower and lower and lower, up to, it goes down to about 6 dB. And when you shift it closer to the house, if the barrier is higher than the emission point, then it gets higher at the end again. So an effective barrier must be close to the best is close to the street, or if it is not, that is not possible, and you have a low emission point, low emission height, then it's possible to put it as close as possible to the house. You cannot put it directly to the house. You must have some space here, and so I said 3 meters is a minimum. It's just my idea. How to calculate this? The directly connection from the emission point to the emission point is this length C, and we have a length A and B. This is the way around the edge of the noise barrier. Then I have factor or number Z, which is just the difference between the way A plus B minus C. And with this I can calculate, oh sorry, this is not here. There is a mistake. I wanted Okay, later I need that. It comes a little bit later. So the next, the calculation is not here. The next point is when I go closer to the window, to the house, it cannot be, there cannot be a wall be erected, but I can strengthen the window. The wall itself normally has a very good sound insulation. The window is the weak point. So I have, I look at the window, for example, here this is a street with the windows in the rooms. Here is, this is not a prison, this shall be a living room, a bedroom, and I have a window. So I have some situation, the window wide opened, and I already said this, in this situation you have 10 dB less than outside. In this situation you have about 20 dB less. And in this situation, when the window is closed, it depends on the window. So when we have a single glass window, we have also only 10 dB. With a, additional 10 dB compared to this. So we have the same situation as here, 20 dB. For example, outside 59, inside 29. With this you gain 20 dB plus this 10 makes 30 dB. This is double window closed. You can sleep even when it's outside more than 60 dB. When you have energy-saving window with a gas filling, with a noble gas inside, you have still better values, up to 30 dB. And with a bigger glass on the outside and also the gas filling, or with a triple window, for example, for the passive house with a U value of 0.6 or 0.7, something like that. You also gain up to 40 dB. And this is nearly the same as the wall itself has. A massive wall normally has, when it's thin, 50 dB, and thicker wall, 60 or 70 dB. So we know that possibility, and now I come back to the walls, and here is a combination shown. There's a wall and a combination between rampart and wall, and you also can have a rampart, and the most important is the upper edge of that. With this, you can get a reduction up to 15 dB within normal economical conditions. When you make a wall which is 10 meter high, it's too expensive. Then it's important that the transmission through this wall or through this barrier is lower than the minimizing or the reduction value dz, which I calculated to 5 to 15 dB plus 10. So for example, if you have a high wall, 15 dB, you need transmission reduction of 15 plus 10 dB. This means 25 dB. And this is not, for example, not possible with a normal wooden wall. You must have a stone wall or some specified walls, and you will hear about that in the next presentation. The calculation for the reduction is depending on the mass which you have. So when you, this is should be a Greek R and rho. And this means when I multiply the thickness of the wall with the density of the wall, I can calculate easily how big the transmission reduction is. I must take in consideration that when I put these walls or these barriers on both sides, the other side will reflect the sound. And the reflected sound also reaches my window. Here is the direct way, which is interrupted. This is the way which the sound takes from the car or what it is here. The indirect way, the reflected way, is this, and it is also reduced a little bit, but not so strong, because there is a mirror source. This is the original source. This is a noise or the sound mirror, and the mirror source is here. And when you take the direct connection from the this is the direct connection from the mirror source to the emission point. you see that the this wall is only a little bit higher, and the reduction dz is much lower. And maybe in this situation you have more noise than you had without any wall. So the only possibility is to reduce this reflection. This means we need a high absorbing material on this side with an absorption coefficient higher than 90%. This is possible with a very good structured wall. For example, you can make a very big wall with structures and flowers in that and something like that. Or when you have not so much money and not so much space, with some absorption material, and also this will be shown by Schütte afterwards. Here I compared the same calculation you saw 2 slides ago or 3 slides ago. I compared different heights, and you see that this, I'm sorry, I did not write down which height this is. I can just tell you this is 2.5 meters, this is 3, and this is 4 meters. These are typical heights of noise barriers. You see again, when I have a emission point of 0.5 meter, this is normal, 0.5 meter over street value, over street level, and an emission point, a window height of the window is 2 meters, relatively low. This does not work on this side. It does not work when you have a second floor. This is normally 4.5 or 5 meters. Then you see this is not rising again here. But in this situation, you have the high reduction value here and the high reduction value here. And I have these three typical heights of walls. Again, I can say we have the standard in Germany. We use or apply the DIN 4109 and the DIN 18005. This is noise reduction for traffic in cities, and we have a special Richtlinie, a guideline, Richtlinie für den Lärmschutz im Straßenbau from the year 1990, the RLS 90. And for streets, and the sound 03 from 2003 for streets. VDI is not a company. This is what is it called? An association. They have several very interesting guidelines, but this is not in the character of a law, but it's very, very good to understand when you read it. So the next, I thought I had, there is one formula is missing, but it's not so important, sorry. So now I come to the calculation of the effects. I think the time is running, and you saw these lines for different sound levels, the sound maps. And when you have such a sound map, here is another place written the airport Köln-Bonn, and here's the same, but for different times, from 10 o'clock in the evening up to 6 for all the time, and this is especially in the midnight, 11 to 1 o'clock in the night. You see the line for the 60 dB is much smaller. We have a very much smaller area. Now this is just to show this. I did not calculate with the airport noise, but I think with this picture you can see that we have different, depending on the noise, we have different areas, and in every area we have some people living there, and there it starts. We can calculate how many people are annoyed or in danger by noise. And now you see this possibility to reduce the noise. This is a little bit difficult to see because two things are inside this. This is depending on the speed. High speed, 120 kilometers for a car and 80 for a lorry, for a freight car, and this is a line for 80 kilometers per hour for a car and 60 for a freight car. And then I have additional one line for a low emission height and for a high emission height. This is for high and this is for low emission. This shows the reduction of the noise by from here to here by a noise barrier, and this is just to show the noise or the annoyance behind the wall. It's not so good to see here. This is in the night, and this is in the day. So we see that. Sorry, this is in the day, and this is in the night. Again, as I showed in the beginning of my presentation, in the night you are higher annoyed by lower levels. This is the same after behind a wall, so you just have to shift the complete level by some decibel from the value which you have calculated to the value with the wall. And now I come to the efficiency. This is a calculation from Switzerland. They changed this possibility to show the efficiency to this. I do not explain this now. Maybe interesting to see the price for some actions which you can do. Here, for example, the surface redevelopment for a reduction of 5 dB costs about 35 euro per square meter. This means when a street is, let's say, 20 meters wide and you have 1 kilometer, you have 20,000 square meters, and you can calculate what the cost is, and you receive a 5 decibel lower noise then. But this is relatively expensive. Also, it is expensive to put a noise barrier in the middle between the street and the building, and to make it too high. So they decided to change to another possibility, and here is the green area, which is okay, and you see this is hyperbolic curve. And when I now calculate, this is a little bit complicated calculation. If you are interested, later on we can discuss this. I look how expensive the noise barrier is for, I think, by 1 kilometer or 300 meters. I must look in my papers, something like that, 300 meters or 1 kilometer. I put a noise barrier in the height of 1 meter, 2 meter, 3 meter, and so on. Less than 1 meter, I did not calculate. The cost will rise linearly, and the number of saved persons, which is a very rough estimation, but when I estimate like this, the number nearly on a hyperbolic curve decreases. So I see that this is indeed the number. For example, here with a 2 meter wall, I have a little bit more than 150 people, and the wall costs per meter about, sorry, this is a kilo euro. The wall will cost about 70,000 euro. And this is quite effective. I have a high effectiveness when I take a very high wall. It will cost, for example, 150,000 euro, and the additional number of people saved is only about 80. So with every euro which I put in this, I can make a high effect when I have a low wall. Okay, that can be discussed. So now I come to conclusions, and I think the time's over, I think. To achieve an optimal improvement of the environmental situation with limited resources. You have only limited resource for construction or paying for activities. You should not do a maximum level reduction at one point, but an appropriate limit, a reduction to an appropriate limit. This is, for example, the 60 dB for all places or for a big number of for big areas, so that you find or reach many people with it. These threshold values are this maximum 60 dB, which should be in the living area, and in the night 40 dB. I think one of the most effective possibilities are relative low noise barriers when the dwelling concentration is high. That is, if you have a very low concentration of persons per square meter or per square kilometer. This is not so good. In my calculations, I have put 5,000 people per square kilometer. This is a concentrated living situation in the city. And the heights of the emission points must also be low. If you have high houses, this is not possible. Then you have, in other cases, to take technical solutions in addition to this, like absorbing street surface and even also noise protection windows are possible. I think when you establish noise barrier by these conditions, this can contribute to save millions of euros in Europe, not in a small country like Europe, but in Europe, by prevention of noise-induced diseases. About that we heard enough, and to save life of, I think, thousands of people, and to improve the life quality of 10,000 or more people who have better quality, better sleeping, and feel better. So, last slide, abstract. I would say these 3 points to reduce unhealthy environmental noise really effectively. Careful planning is needed, and you must know much about the physical origin, the propagation conditions, and also for the physiological consequences, the illnesses which come from the noise. This all must be known. When you deal with this, for this purpose, all these measurement principles and the physics of spreading and damping and so on, and the organic mechanisms in our body must be well known. And I think from these thresholds which you find here, which should be, I think, in the region of this 60 dB, we can derive the dimensions of noise barriers quite well to make it very effective. Thank you for listening.
Thank you. And does anyone has any questions? Kas kellelgi on küsimusi? Jah, seal taga on üks.
Milliseid müra vähendamise meetmeid on võimalik kasutada impulsmüra korral?
Thank you. Impulse noise can be measured by a normal sound level meter, which integrates the modern class 1 meters do that. Important is, I think, that you must measure the height of the impulse. By German consideration, or by German laws, this may not be higher than 20 dB over the average value which you calculate. If it is then higher, then, for example, you have only one car in the hour, this car has a maximum level of, let's say, 60 dB. And the average value which you calculate or your meter produces for you is 37 dB. This is 23 dB higher. If it is more than 20 dB, you must put an additional term of 3 up to 6 dB, depending on the height, to this. So you come from 37 to 40, for example. But this is relative seldom. Normally, when you have a number of, let's say, 5 or 10 or 20 cars, it is the average value is so high that the maximum value of the impulse is not higher. Maybe this is the answer, I'm not sure, for your question.
Aga kui on lasketiirudes relvad,
but yeah, About shooting range noise, I did not do many calculations. I only once had a project for a shooting hall. There I calculated because there were a big number of shots in a short time. But when you have a shooting range where for example, there is one shot and then several minutes break and then again one shot, this pulse is much, much higher than the average. And I cannot say exactly what we should do then, which value should be applied. I concentrate on this traffic noise, and I'm sorry I cannot give you a complete answer to that.
Kas on veel küsimusi? Ja, sealsamas taga on veel.
Minu küsimus on, et mitu detsibelli suureneb liiklusmüra, kui liikluse keskmine kiirus tõuseb 90 kilomeetrilt tunnis 110-le?
Yeah, thank you. I would say about 2 decibels. When you want to know it exactly, I can go to the... one moment. Here you find this. Oh, sorry. Nah. Here you find the line for the 90 decibels, and there the 110. And now it depends on the part of freight cars, and if you have no freight cars, only cars, you have here, for example, compared to 100 dB at 90 you have -1, and at 110 you have +1, so it's relative exact 2 dB more.
Kas on veel küsimusi?
Hello, I will ask in English, is it okay? Or it's...
Yeah.
Could you please explain this open window and closed window system you have in Germany? How those noise limits are really like specified in your standard? Is it like with open window or you have it with closed window?
In the calculation, we calculate with a closed window. Yeah? When in Germany, in between, with every appliance for building a house, you have to define the mechanical structure and the heat protection and the fire protection, and also in between you have to define the sound or the noise situation. And then you have to calculate this surface of the house consisting of wall and window, and you calculate with a closed window. If somebody then opens the window by himself, it is more noisy and its own thing. Normally, I must say, because I do also the energy saving, when you have in the winter situation, you should keep your window closed and open it only for a few minutes a day. And these are not the minutes when you sleep. But I personally propose that also in Germany we should, in the future, have ventilation systems which give fresh air to the room without open window.
Tundub, et küsimustega on selleks korraks kõik. Veel kord aplaus professor Jan Middelbergile.